Welcome to Wireless Packet Analysis with Eye P.A. In this webinar, we're going to start by talking about some of the differences between 2.4 and 5 gigahertz. We'll note some differences in the way the channels are laid out in those two different bands. We'll talk about device compatibility, and then we're going to jump into the basics of packet analysis. And that is talking about airtime arbitration, how clients decide who gets to talk next. We'll start with the half duplex nature of Wi-Fi and how only one device can talk at any time. And then we'll talk about the different wireless frame types. And then we'll jump into a time of live demo with some packet analysis software. We'll do some throughput testing and make some comparisons between the two bands to see how well they perform. And hopefully by the end of this webinar, you will not only be trained up in how to use Eye P.A, but if you're looking at buying it, hopefully you'll also kind of have an idea of what it does to help you make that buying decision. So welcome to the webinar. A couple of quick things I wanted to make note of before we get the webinar started is if you have any questions, feel free to use the question tool. More than happy to answer your questions through that tool. Some dialogue can really make for a great webinar, so I'll look forward to seeing your questions. Next, if you experience any audio or video problems, just let me know. We can run into problems like that on these webinars. There are a lot of technical limitations to surmount when presenting a live webinar, when doing packet analysis and things like that. But if you have any trouble seeing the slides, if they're not updating or if the audio is garbled, just let me know and we'll go ahead and get that fixed. And just a quick introduction, my name is Joel and I take care of most of the training and support here at MetaGeek. I don't take care of all of it because MetaGeek is unique in that we actually bring everybody in the company comes in and helps with support. Every day, somebody different, whether they be from the marketing team or from the development team, everybody pitches in and helps with support. If you open up a support ticket, there's a 50-50 chance that you'll talk to me or you'll talk to whoever's helping with support for the day. That might be a developer. That might be the guy who does our web development for us. That might be our marketing gurus. It's hard to say. And if you ever have a question, feel free to open up a support ticket at support.metageek.net. Believe it or not, that actually has a higher interrupt on my interrupt list than even my personal email. So we try to answer those as quickly as possible. I'll put this information up again at the conclusion of the webinar. You can also contact me on Twitter if you'd like to ask a quick question or something like that. My Twitter feed is about 50 to 60% Wi-Fi related. So just keep an eye on that if you're interested in that. So with that, let's go ahead and get the webinar started. So the first thing that I want to talk about is the half duplex nature of Wi-Fi. And this is really important when we are looking at doing packet analysis. So many of us are familiar with Ethernet, and Ethernet is a full duplex standard, which means with an Ethernet cable, we can send traffic in two directions at the same time. We can send traffic east and west with Ethernet. It's kind of like a two-lane highway. With a two-lane highway, we can send traffic in two directions. But with Wi-Fi, it's a little different. Instead of a two-lane highway, it's more like a one-lane highway because any two devices that are on the same channel have to take turns talking. On any given channel at any given time, only one device can talk at a time. So they have to take turns talking. And it's kind of like a human conversation as well. Let's say that you are talking with a friend and you try to say something and they try to say something at the exact same time. Only one device can talk at a time. If only one device can talk, then they're going to have to take turns. If you say something and your friend says something at the exact same time, then you're both just going to interrupt each other. You're not going to understand what they're trying to say, and they're not going to understand what you're trying to say. Only one person can talk at a time. It's much the same way with Wi-Fi. We've got these two devices in this example that are on the same channel. I do apologize. My slides do tend to jump around a bit due to my mouse. It's overly sensitive with scrolling. So the Magic Mouse is Apple Magic Mouse is not conducive to giving presentations, unfortunately. So my slides do tend to hop around a bit. So what we see in the Wi-Fi world, the world of Wi-Fi, is that we see that devices take turns talking. Right now, this device, this tablet is transmitting some data to this access point. And while that transmission is occurring, the access point is going to be quiet and it's going to wait for its turn to talk. But on receiving that data frame, it's going to reply with an ACK. It's going to acknowledge that frame. It's going to say, hey, yep, check, I received that frame. Here's a notification that I received that frame. And what can happen in these circumstances? Let's say that the tablet here transmits that data frame, but it never makes it to the access point for whatever reason. Maybe it's a little bit too far away and it just got kind of garbled by the time it got there, so it wasn't a readable frame by the time it reached the access point. The client's going to sit there for a second and it's going to go, okay, well, I never heard an acknowledgement, so it must not have received the frame. So it's going to wait a short amount of time and it's going to transmit that data frame again. And it's going to keep sending that frame over and over and over again until finally the frame is received by the access point, and the access point will acknowledge that the frame was received. When you boil packet analysis down in the Wi-Fi world, this is the root of it all. This concept right here is what commands packet analysis, and especially for us with Eye P.A. So we're going to come back to this in just a second, but let's go ahead and take a look at the differences between 2.4 and 5 gigahertz. Understanding the differences between these two are very important, whether you're doing just about anything in Wi-Fi, especially packet analysis. So let's take a look at the 2.4 gigahertz. First, in the 2.4 gigahertz band, we're going to see greater range, and that's because the 2.4 gigahertz wavelength is longer than the 5 gigahertz wavelength. The 5 gigahertz wavelength is much shorter. The wavelengths are much closer together. So it doesn't do nearly as good of a job at punching through objects. It attenuates faster than 2.4 gigahertz. So we see that it has a lower indoor range. Now, outdoors with 5 gigahertz, it's really going to have about the same range. It's indoors where it really matters. It's when it encounters things like people and walls and doors and desks and computer monitors and things like that really soak up that 5 gigahertz. When you're looking at compatibility for 2.4 and 5 gigahertz, you're going to see that 2.4 gigahertz has a much wider compatibility. In fact, pretty much all Wi-Fi devices out there are going to support 2.4 gigahertz. And this goes all the way back to the days of 802.11b and 802.11a. 802.11b and 802.11a were actually introduced at the exact same time in 1999. But 802.11b was an improvement on a standard that already exists in 2.4, the original 802.11 standard. 802.11b kicked us up to 11 megabits per second, down from 1 megabit per second. So it was about 11 times faster. Whereas 802.11a opened up the brand new 5 gigahertz spectrum, a brand new slice of spectrum for 802.11, and it got us a maximum data rate of 54 megabits per second. So it was about 5 times faster. But for several reasons, 802.11b ended up kind of winning the battle. Many of us remember back to the days of VCR versus Betamax. My parents had a Betamax player, and they had about 3 or 4 movies for the Betamax player. VCR ended up being much, much more popular, and it kind of took off, and it won the format war. More recently was HD, DVD, and Blu-ray. Blu-ray ended up being much more popular, and all the companies that were supporting HD DVD, like Toshiba and Microsoft, all backed out, leaving the format to die. Now Blu-ray is the dominant optical solution for video playback, as well as several other things now, like video games and things like that. So 802.11b and 802.11a were kind of in a battle to see which one would be more popular, and 802.11b ended up winning for several reasons. There's several reasons why 802.11b ended up winning the battle. First off, back then, Wi-Fi wasn't even called Wi-Fi yet. It was just called 802.11, and it was primarily being used for barcode scanners in warehouses. And in an environment like that, high performance isn't really that important, but what is important is range. 802.11b was in the 2.4 gigahertz band, so it had a range of about 300 feet, whereas 802.11a only had a range of about 90. So it was more expensive to deploy because you needed more hardware to cover your warehouse. Second, 802.11b was simply an extension of what we'd already been doing in 2.4 gigahertz. We'd already established the 802.11 hardware and things like that in the 2.4 gigahertz band, so it was cheaper to make those chipsets. 802.11a, on the other hand, was brand new hardware, and it wasn't as cheap to manufacture. And what ended up happening was that 2.4 gigahertz ended up being a lot more popular than the 5 gigahertz band, and we're still feeling the results of that today. Today, if you go to the store to buy a Wi-Fi device, you are guaranteed 802.11b, G, N compatibility. Those are all 2.4 gigahertz standards. Whereas if you want 802.11a support, or more recently 802.11ac support, you have to check the packaging specifically to make sure that it supports those standards. If you see 802.11a, then you know it's a dual band device. Now, this problem is getting better. We're seeing more and more dual band devices on the market. Apple actually is a great example of this. Apple's been doing a great job of making sure that their devices include dual band capabilities. The iPhone 4S, I have one here sitting on my desk for my Wi-Fi lab. It's a 2.4 gigahertz BGN only chipset. But starting with the iPhone 5, Apple started putting a dual band radio in pretty much every mobile device that they sell. Every iPhone 5 and newer has an 802.11a BGN radio on board. And another example is the Google Nexus line. They put their first dual band radio in the Google Galaxy Nexus, which was an Android phone. And then in 2012, they released a 7-inch tablet called the Nexus 7, and it was incredibly cheap, $199. We've got 2 of them at home, but it has 802.11 BGN only. In 2013, Google refreshed the tablet. They introduced the 2013 model, and it has 802.11a BGN on board. So this problem is getting better, but you're still going to see a lot of inexpensive Windows laptops and cheap Android phones and tablets like the Moto E and the Moto G by Motorola. Even though they're brand new devices, both of them released within the past year, neither of them have dual band radios on board. So that's something to watch out for. Some other things to take note of in the 2.4 gigahertz band. I apologize for my slide switching. It doesn't like to give me control of the mouse and give me my annotation abilities back. In the 2.4 gigahertz band, some other things that we need to watch out for are congestion from other Wi-Fi devices. Since it's kind of been the default band for so long, the 2.4 gigahertz band is highly congested with Wi-Fi. And if that band has good range for Wi-Fi, it has good range for non-Wi-Fi as well. We see a lot of non-Wi-Fi devices there. Cordless phones, wireless video cameras, Zigbee devices, microwave ovens. The list of devices that operate in the 2.4 gigahertz band goes on and on and on. We see lots of interference from other devices. And then finally, perhaps the biggest problem with the 2.4 gigahertz band is that there are only 3 channels that don't overlap. 3 non-overlapping channels. And you might be thinking to yourself, well, hang on a second, Joel. I'm pretty familiar with the 2.4 gigahertz band, and I know that it actually has 11 channels. So what are you talking about there? Well, you're right. It does have 11 Wi-Fi channels, but here's the problem. The 2.4 gigahertz band is only about 60 megahertz wide. In all, the usable space that we get for Wi-Fi is only about 60 megahertz wide. And each Wi-Fi channel is 20 megahertz wide. Each Wi-Fi channel is 20 megahertz wide. And when you do the math, you realize, wow, there's really only room for 3 channels there. So how do we pack 11 channels into the 2.4 gigahertz band? Well, we do it by doing partial overlap. If we were to increment up 5 megahertz from the center of channel 1, we're going to find the center of channel 2. And if we draw a box there to show where it is, we can see that channels 1 and 2 overlap by about 75%. And this is true for many of the other channels in the 2.4 gigahertz band. That's why we say that the only 3 channels that don't overlap are 1, 6, and 11. And we're going to talk about that a little bit more coming up here. In the 5 gigahertz band, we have 24 channels that do not overlap. Now, each one of these channels is still 20 megahertz wide, just like their 2.4 gigahertz counterparts. But since the 5 gigahertz band is so wide in comparison, I have to squish it down here to fit it on the slide. And you'll often see 5 gigahertz channels represented like that. 5 gigahertz is much, much quieter than the 2.4 gigahertz band. If you look at a spectrum analysis capture where the color indicates activity, we can see that there is a ton of empty space in the 5 gigahertz band. There's a lot of space that we aren't even using yet. Whereas in the 2.4 gigahertz band, things are really, really crowded, and that makes for much worse performance. And we're going to see the results of that here later in this webinar. So back to the half duplex nature of Wi-Fi. We talked about how only one channel on any given channel, one device on any given channel can talk at any given time. And instead of having just one access point and one client like we did earlier, let's throw 7 Wi-Fi devices onto this channel. We've got our access point and we've got all of our different client devices here. And right now, iPad number 4 is currently transmitting some data to the access point. While that transmission is occurring, all of these other devices are going to be quiet. They're all going to be quiet and they're all going to wait for their turn to talk. If any of them were to talk right now, they would interrupt that transmission and it would have to be resent. Only one device can talk on any given channel at any given time. But wait, there's more. There's something else that we need to consider here. How about the amount of devices on this channel? Right now, we have got 7 Wi-Fi devices on this channel. But what if we had 30? What if we had 50? Or maybe what if we had 100 devices on this channel? The more devices you add to a channel, the smaller and smaller everyone's transmit opportunities get. It's kind of like taking a pie to a party. If you take a pie to a party and there's 8 people at the party, everybody's going to get a pretty reasonably sized slice of pie. But if you take a pie to a party and there's 30 people at the party and you try to cut that pie up into 30 pieces, everybody's going to get a tiny slice of pie. If somebody offered me a 30th of a pie, I'd probably say no thanks, not really worth my time. But wait, there's one more thing that we need to consider when we're thinking about devices on a channel. I apologize, it's not giving me my annotation tool back. Let me see if I can get it back really quick here. There we go, got it. When we're thinking about all the devices that we have on a channel, not only do we need to think about how many devices are here, but we also need to think about speed. How fast are these devices talking? In Wi-Fi, we can use different data rates, and when we're further away from an access point, we need to use a data rate that our access point can understand. If we're really far away from the access point, we might have to slow down. Like maybe this device who's way out here might have to slow down and use a slower data rate, like maybe 1 megabit per second, because he needs to enunciate so that he can be heard by the access point. Meanwhile, all these other devices, since they're close by, they might be able to maintain some nice fast data rates, like maybe 72 megabits per second, or maybe 54 megabits per second, or maybe even 24 megabits per second. It's not as fast, but it's still relatively fast compared to 1 megabit per second. When you're close to an access point, you can maintain those fast data rates, but when you're far away, you have to slow down and enunciate so the access point can hear you. And here's the problem. If we're all sharing time talking here, if we are all competing for time to talk, this device over here, this slow talker, is going to take 72 times longer to say the same amount of data as this device. 72 times longer to transmit the exact same amount of data. And that's going to force everyone else to wait longer. It's going to force everyone else to wait longer to say what they need to say. So we need to preserve airtime. We need to make sure that everybody has a reasonable amount of time to talk. And we do that in several ways. We do that by making sure that there aren't too many devices on a channel, and we make sure that all the devices are talking fast and that no one is hogging time talking by talking slowly. So let's talk about the different types of interference. First, we've got co-channel interference. And this is where we've got devices all politely taking turns talking on a channel. They are all competing for time to talk, but at least it's a nice, polite conversation. Next is adjacent channel interference. We touched on this briefly, but in this example, we've got a network on channel 4, a network on channel 6, and a network on channel 5. If you were to visualize those with a Wi-Fi scanner, we would see that we've got our channel 6 here, and then we'd see that channel 5 was about here, and then we'd see that channel 4 is about here. All 3 of those networks are partially overlapping. And instead of taking turns talking politely like co-channel interference, they're just going to yell over each other. Co-channel interference is kind of like a polite dinner table conversation. As long as no one hogs time to talk, and as long as the table isn't too big, everybody's going to take turns talking politely, and it should work pretty well. But with adjacent channel interference, instead of taking turns talking politely, they're just going to scream over each other. They're just going to yell over each other. It's kind of like going to a restaurant and getting a table with some friends. That's a lot like co-channel interference. You're going to politely take turns talking. But adjacent channel interference occurs when another group of people move into a table next to you. Pretty soon, the restaurant's gotten noisier. They're not taking turns talking with you because they're not a part of your conversation. They're having their own conversations at their own table. And then finally, there's non-Wi-Fi interference. This comes from devices like cordless phones, Bluetooth devices, wireless mice and keyboards, analog video transmitters. The list of devices that goes on, that talks in the 2.4 gigahertz goes on and on and on. And these devices are also competing for time to talk. They need time to talk just like Wi-Fi. And typically, they aren't going to be nearly as polite. So different tools for different jobs. Insider, being a Wi-Fi scanner, shows you where the wireless networks are. So in this example, we can see that there's a network here on channel 1, and there's another network here on channel 2, and they are both partially overlapping. They're just going to yell over each other with adjacent channel interference. We can also see that there's two networks here on channel 6, and that's good. We know that they're going to politely take turns talking. Of course, we want to avoid that if possible, but that's definitely better than adjacent channel interference. And then finally, of course, being on an open channel by yourself is the best. With a spectrum analyzer, you can see the non-Wi-Fi interference. Like if we had a cordless phone here talking on the same channel as where your wireless network is, you can mitigate that problem. You could possibly move that device away. You could say, well, let's switch it up to a different channel. Or maybe we just need to move our Wi-Fi network down to a different channel to get away from it. Or perhaps we just need to unplug that device and get rid of it, replace it with something newer that's a bit more Wi-Fi friendly. So what does packet analysis show us? Packet analysis gives us some special details into the channel. With a Wi-Fi scanner, it's great because you can see where the networks are, but the problem is what's really happening on channel 6 right now? What is actually happening there? Do we really know? With a packet analysis tool, we get to see all the details. We get to see the access points. We get to see the laptops and the tablets and the smartphones. We get to see all the activity that's occurring on the channel. We get to also see the MAC addresses for individual wireless clients. We get to see the utilization of independent 802.11 stations. We get to see how often they're talking, how often they're utilizing the air. We get to see how often our access points are utilizing time on the channel. We get to see those retransmission rates. If we have to resend our frames, we get to see how often we're having to do that, how often we're having to repeat ourselves, and we get to see the data rates for all the conversations that are occurring. We get to see how fast or slow wireless clients are talking. So what we've done here is we've taken our packet analysis tool, which is called Eye P.A, and I'm going to dive into this tool in depth in just a few minutes. And we did a throughput test comparison. We took a dual band Android phone. This was the Google Galaxy Nexus. It's an older phone, but it checks out. It's got 802.11a, B, G, N support, so it's dual band. And we streamed a high definition YouTube video on it over the 2.4 gigahertz band on an enterprise grade access point. And what I've done here is I've broken out some of the stats that we've gotten so that you can kind of see what we're going to get from a packet analysis tool when we perform a test like this. We can see that during that packet capture, while we were capturing packets on that channel during that test, we saw 27 unique SSIDs, 27 unique networks on that channel. We can also see that we saw 311 wireless clients. 311 other Wi-Fi devices talked, and we can see that for the whole channel, for the entire length of the capture, we can see that we saw a retry rate of 39%. So nearly 40% of the time, all of the devices on this channel had to repeat themselves. For the individual client, not just the whole channel, we can see that we maintained a data rate of 11 megabits per second. 11 megabits per second is an 802.11b data rate. That data rate was invented in 1999. And since there was so many problems, so much going on this channel, we had to slow down and use that slower data rate to communicate with the access point. And we can see that for our individual wireless device, we can see that our retry rate for it was 37%. 37% of the time was spent resending our frames. We used the same hardware, the same enterprise grade access point, the same Android phone, and we did this test in the 5 gigahertz band to see how it would compare. And in this test, again, we've broken the data out here so that you can see it. We saw on this channel during the packet capture in the test, we saw 2 SSIDs. We saw 43 clients instead of 311 clients like we saw in the 2.4 gigahertz band. We saw 43, a sixth of the amount of clients. And we also saw that our retry rate was a quarter. It was 9%. And we can see for our individual client, we can see that our data rate was 51 megabits per second. That's a nice, fast 802.11g data rate. So we got on the air, we said what we needed to say, and we got off the air much faster in the 5 gigahertz band. We saw much greater performance, and we were able to see this with a packet analysis tool. We were able to see what was going on. So let's dive deeper into packet analysis. Let's take a closer look at what's going on in the world of Wi-Fi packet analysis. In the world of Wi-Fi, you're going to see 3 frame types: management frames, control frames, and data frames. And in IPA, we color each one of these differently. And if you forget which color is which, there's actually a cheat sheet built into that's built into IPA. In the filters toolbar, we can see that our management frames are purple, our control frames are orange, and our data frames are blue. And you can even see the subframe types as well if you forget what subframe type belongs to which frame type. So let's go through each one of these frame types and let's look at all of their frame subtypes. Let's start with management frames. My colors are a little messed up from importing my slides into a different tool. Apologies, I didn't catch that before. I caught it on some other slides, but not on this one. So what do management frames do? Management frames help stations join and leave a wireless network. They help stations get on and get off a wireless network. Some examples of this are beacons. A beacon frame is simply an access point's announcement of its existence. For example, I have an Apple Airport Extreme at home, just my home Wi-Fi access point, and continually it sits there every 100 milliseconds or so. It says, hey, I'm Joel's network. I'm here. I support this type of encryption. I support these data rates. You can connect to me. And then it waits about 100 milliseconds and goes, hey, I'm Joel's network. I'm here. I support these types of data rates. I support this type of encryption. You can connect to me. A beacon is simply an advertisement of an access point's existence. When you get your phone out of your pocket and you open up the Wi-Fi settings to see which networks are nearby, it's able to see those because your phone is listening for beacons, and all the Wi-Fi devices around you, all the wireless networks rather, are beaconing. They're beaconing to say that they are there. Next is a probe. And a probe is kind of the opposite of a beacon. When I'm at home with my Android tablet and I'm connected to my home Wi-Fi network, as soon as I leave that network, let's say I jump in the car to head downtown to go to work, my tablet's going to lose sight of Joel's network, and it's going to start probing for familiar networks. It's going to say, "Hey, MetaGeek, are you there?" Okay, nothing from MetaGeek. Hey, Joel's network, are you there? And then when I arrive at MetaGeek, it might say, hey, MetaGeek, are you there? And MetaGeek will reply with a probe response. It'll respond and say, hey, yep, I'm MetaGeek, I'm here. Probes help us get connected to wireless networks faster. They help us get associated to a network much more quickly because our devices are actively looking for familiar wireless networks. With the right packet analysis tools, you can sit at a busy place like an airport and you can watch devices probe for network all day long. It's pretty fun. Next are authentication and association frames. These are pretty self-explanatory. They help us get authenticated and associated to a wireless network. Association is when we say, hey, I am now part of Joel's network. We are associated to each other, and we are going to have a conversation. So management frames help us join and leave a wireless network. The next type of frame that we want to look at is a control frame. Control frames, they do just what the text says. They control the RF medium, and they make sure that data and management frames get delivered properly. Some examples of this are an ACK, or an acknowledgement. We actually talked about ACKs a little bit earlier. We see a constant process of data, and then the receiving device will acknowledge it with an ACK. It will say, yep, I received that data frame, I got that frame. 802.11n came along and made block acknowledgements mandatory. So now instead of going data, acknowledgement, we can go data, acknowledgement. We can acknowledge more than one frame at any given time. And then finally, there's RTS and CTS. And we actually had a great example of why we need RTS, CTS, request to send and clear to send here at MetaGeek just the other day. Here at MetaGeek just the other day, I was standing in a doorway between two rooms. Lael was in the kitchen, and Rich was standing out with all the developers. And I was standing in the doorway, and they both said, "Hey, Joel," at the exact same time, and both started talking to me. And I had to go, whoa, guys. There's two of you are talking to me at the same time. That's because Rich and Lael, they couldn't see or hear each other. They didn't know that the other was there, so they both started talking at the same time. If we would have been using RTS, CTS, now, in a human conversation, it'd be kind of weird, but if we were using RTS, CTS, we would have avoided that problem. Lael would have said, "Hey, Joel, can I talk to you?" And I said, "Yes, Lael, you can talk to me." And that would have signaled to Rich that there was already a conversation occurring, and so he wouldn't have accidentally interrupted that conversation. We use RTS, CTS when clients can't hear each other. If we've got two clients that can't hear each other, but they can both hear the access point, RTS, CTS will kick in, and we'll make sure that those devices don't start talking over each other. Finally, Finally, are our data frames. This is the whole reason why we have a wireless network at all. What do these do? They carry higher level protocol data. They make sure that our higher level data from the upper layers of the OSI model get delivered. Examples of these are data frames, quality of service data frames, and then finally null data frames, which are kind of funny because they're not actually a data frame at all. We use these for things like power save polls and things like that. They don't actually carry data, but they end up getting classified as a data frame anyway. These are the only frames that get passed over to the Ethernet side of the network. When these frames are the only ones that traverse the access point and get through. The management frames and the control frames are Wi-Fi specific. We do not see them on the wired network. We only see data frames make it over to the wired network. So let's take a look at a wireless conversation between one access point and one client. Let's see what this conversation would look like. So we're going to start by assembling our frame, and then we're going to check to see, is the channel idle right now? Is the channel currently idle? Is there anyone talking on the channel? And excuse me, we just scrolled through a bunch of slides. If the channel is not idle, then we're going to wait a random amount of time. And then we're going to check again to see if the channel is idle. And if it still isn't idle, we're going to have to wait longer and longer and longer and longer for that channel to free up. Finally, we might get an opportunity to talk. It's now our turn to talk. So we are going to transmit that data frame, and then we're going to be done. If RTS-CTS is enabled, request to send and clear to send, then we've got a couple extra steps involved that we need to get through. So maybe we assemble our frame and we check to see if the channel is idle, and if it's not, we're going to wait our random amount of time, and we're going to wait until finally we get an opportunity to talk. So now that it's our turn to talk, now that it is our turn to talk, we are going to transmit an RTS. We're going to say, hey, can we request to send? Can we send a frame right now? If we don't receive a clear to send, then we are back to where we started. If we do receive a clear to send, then we're going to transmit our application data, and then we're going to be done. And this happens every single time we need to send a frame. So this is for one access point and one client. So let's take a look at what this might look like with more than two Wi-Fi devices on a channel. In this example, we have 6 wireless stations here. Now remember, a station can be either an access point or a client. It doesn't matter. It doesn't matter whether it's an AP or a client in this example. So we've got station 1, station 2, 3, 4, 5, and station 6. And station 6 is just finishing up sending some data right now. It's just finishing up transmitting some data. Then we're going to have a CIFS, a short interframe spacing. And then station 5 is going to reply with an ACK. It's going to acknowledge that data frame. Meanwhile, stations 4 and 2 both need to transmit some data. So they're going to roll the dice to determine who gets to talk next. Station 4 is going to roll 9 random backoff slots, and Station 2 is only going to roll 7. They're both going to sit there and watch those backoff slots go. It's going to go 1, 2, 3, 4, 5, 6. And then Station 9 was holding out for 9 backoff slots. But since Station 2 only rolled 7 backoff slots, it's going to go, okay, no one said anything yet, so it's my turn to talk. Station 4 is going to be kind of disappointed, but he's going to wait because he did not win that time. He did not get the opportunity to talk. Station 2 and Station 1 have RTS-CTS enabled, so Station 2 is going to transmit the RTS. It's going to transmit the RTS, and Station 1 is going to reply with a clear to send. Yep, you are clear to send. Now, when this RTS was transmitted, notice that Station 4 did something. It defers. It saw that another device is talking, but it's keeping its backoff counter of 2. It goes, okay, I only have 2 random backoff slots left before it's going to be my opportunity to talk. When the CTS was transmitted, it let everybody know, hey, we're about to have a conversation over here. Everybody be quiet. So now Station 2 gets to transmit its data, and then Station 1 replies with an acknowledgement, and that conversation is done. All of those backoff timers have now expired. Now it's Station 4's turn. It's only got 2 backoff slots remaining, so it's going to count to 2. 1, 2. Okay, now it's my turn to talk, and it's going to transmit its data. And notice that when it transmits its data, Notice what station 2 does. It rolled 10 random backoff slots, so it's going to defer, and then next time around, it's only going to count to 8 before it starts transmitting. Station 3 sends an acknowledgement, and we're done. This process is happening constantly. In fact, this process is happening several million times a second on any Wi-Fi device at any given time. If you have a phone in your pocket right now with Wi-Fi on, it's doing this for every frame type out there, even a beacon. Even whenever a beacon happens, a device is going to check, okay, is anyone talking right now? Nope, no one's talking, and it's going to send its beacon to let other devices know that it's there. They even arbitrate for things like that. And if this doesn't, this is one of the things that just absolutely amazes me about Wi-Fi. This makes me appreciate Wi-Fi a whole lot more. So how do we visualize this? How do we use this data now that we know how all this works? How can we visualize it and put it to work for us to help us improve the performance of our wireless network? Well, we can do that with a packet analysis tool. And we were down at a packet analysis conference. It was called Wireshark. Wireshark is a user and developer conference for SharkFest rather. SharkFest is a user and developer conference for the famous packet analysis tool Wireshark. It's a free open source tool. And while we were there, we thought, you know what? Wireshark is incredible. It's one of the greatest tools out there, but it doesn't help you visualize what's going on in your wireless network. And maybe we can come up with a solution for that. And that's when we came up with this tool called Eye P.A. Eye P.A stands for Eye Packet Analysis because it's a visual packet analysis tool. And we use multi-layered pie charts in it that kind of look like an eye, and our developers also really like beer. So we visualize data in Eye P.A through different colors. We talked about the frames and the subframe types earlier, and we color those frame types. We can see here that this blue represents data frames. This orange represents our management or our control frames, and the purple represents our management frames. So we're using different colors to represent those different frame types. We also use a multi-layered pie chart to represent the data. And each one of these layers of the pie chart represents a different set of data, a different amount of time, or a different classification on the air. So if we look at the innermost frame is either our ESSID or our radio group. You can group together access points by radio, which is basically a virtual access point, or you can group them together by ESSID. So if you have multiple access points with all the same name, you can group them together. The next layer is our individual access points. That's our individual access points. Like we have got an access point right here. And what this slice of the pie chart shows us is it shows us how much time that device took up talking. The pie chart represents 100% the amount of time used, and we can see how much time this particular access point took talking. The next layer are our individual clients. We can see each client and how much time each client took up talking. And then finally, the outermost layer is our subframe type. We can see that these purple ones are our management frames, and we can see that these orange ones are control frames. So we can see exactly what's going on. We also have a time graph to show you how much of the airtime was used over time, and we also have awesome data tables all over the place that you can export for use in other tools. We have tried to reimagine packet analysis with Eye P.A by highlighting trends, giving you fast and intuitive filtering, and awesome conversation analysis. So what I want to do now is let's go ahead and jump into a live demo of Eye P.A. So I've got a virtual machine here running Windows 8. This is just a virtual machine running on my MacBook Air. So let's go ahead and start up. Eye P.A. I just started up Channelizer on accident, so I'll have to close that in just a moment. And I'm going to do my packet capture in Windows with a special packet capture tool called an Eye P.A NX. This is a product made by Riverbed, and it's a Wi-Fi chipset that's specifically designed for doing packet capture in Windows. Doing packet capture in Windows is very challenging. You can't do it with a normal Wi-Fi adapter because a normal Wi-Fi adapter in Windows will leave out all of our management and control frames, and it'll only give us the data frames that are destined for your device. So let me go ahead and connect this device to our virtual machine. Let's try restarting Eye P.A. Since it is a virtual machine, I do occasionally, USB is always a little bit strange on a VM. Let me try unplugging and plugging my Eye P.A back in. This will just take me a moment. Success. Okay, great. So now that we have our AirP-CAP NX connected to Eye.P.A, you can see that we can perform our packet captures from directly within Eye.P.A. Now, you can also use PCAP files from other sources as long as they have their radio tap headers or their PPI common headers. You can get packet captures from the Wi-Fi diagnostics tool in OS 10 if you have a Mac. That's a great way to get wireless packet captures. You can also get packet captures within Linux if you have a wireless adapter that supports monitor mode in Linux, and also from an enterprise grade access point. So what we're going to do here is I've got two wireless clients here. One of them is connected to the 2.4 gigahertz SSID on an access point, and one of them is connected to the 5 gigahertz SSID on an access point. So what we're going to do is we're going to start with the 5 gigahertz SSID. So let's take a look. Actually, let's start with the 2.4 gigahertz one. So we're on the 2.4 gigahertz band with channel 6 selected. So we're going to start our packet capture. And now I'm going to perform a speed test. This client is a first generation Motorola Moto X connected to the 2.4 gigahertz band on an access point. We can see our file size is jumping up rapidly as we're performing our throughput test here. So let's let it gather about 2 megabytes worth of data. We'll let it gather about 2 megabytes worth of data, and then we'll go ahead and stop the throughput test. So there's about 2.3. That's good enough. So let's stop the packet capture and let's take a look at this conversation to see how we fared. Let's see what happened during the course of this capture. If I hover my mouse here, I can see we're grouping by radio right now. So let's switch to grouping by ESSID. So now we are grouping by SSID, and we have an SSID here called MetaGeek Lab 2.4, and we can see that it is on channel 6. And if we go one more layer in, we can see the specific access point. It's just one access point in this ESS, so technically it's not an ESS. We can see that we had a retry rate of about 41%, and we can see that it took up about 3/4 of the total amount of airtime used. If we highlight it by hovering our mouse, we can see that about 3/4 of the airtime were used. If we go one more layer in, we can see the individual client, and we can see that this client used about half of the total airtime that was used. And we can see that the majority of that was quality of service data frames. If we look at this device, look at the retry rate. We had to resend our frames 64% of the time. So let's drill down into this network to take a closer look. I clicked on it. So now the network is in the middle and our clients are the second ring out and our subframe are the third ring out. So we can see that here's our Moto X, here's our Android device. We can see we've got some multicast and broadcast frames, and there's an Intel device here that was communicating with it as well. But we can see that this device took up the majority of the airtime. Now, on the airtime overtime graph, we can see that we were peaking at about 100% airtime usage. And we can see that we had a period here where there was no communication. And then right here, this is where we started our throughput test, and our throughput test took off. What we currently have filtered or drilled down into or selected in Eye.P.A right now is what we've got highlighted up here in the bright yellow. The dark yellow is stuff that we don't have selected right now, stuff that we do not have selected in the tool. We can see that we spent about 58 or 60% of our time sending frames at 1 megabit per second. We did hit 24 megabits per second about 5% of the time, and then finally the maximum was 36 megabits per second. We weren't able to talk fast. This conversation was slow. Our effective data rate was only 1.3 megabits per second. That's an average of the speed of our data frames. And we see that our retry rate is 64%. This conversation was not quick and it was not efficient. If we click on this device to drill down into it even more, we can visit the Packets tab and we can see this conversation on a frame-by-frame basis. We can see where we were trying to send quality of service frames and they were getting acknowledgments. And we can see where those retries were occurring. We can see where we were having to resend our frames. This conversation was not a very good conversation. It did not happen very quickly. So let's go ahead and test in the 5 gigahertz band now. Let's switch to 5 gigahertz and let's switch to channel 165 and let's start that capture. We won't save our existing capture. And let's start up our client device here. And let's begin the throughput test. And let's see how the 5 gigahertz compares to the 2.4. So we can see that we're gathering frames slowly, and then all of a sudden they take off like a rocket because now we are moving a lot of data through the air. We've already captured about 2021, we're going to hit 25 megabytes worth of packet capture data. So let's go ahead and stop the capture. And what you'll notice is that IPA actually parses this data before it even shows you the capture. And that's what makes for really quick navigation and really quick filtering in IPA later on. So let's let it finish opening the file. I am doing several things with my MacBook Air right now. So we can see here where I was getting the packet capture started, and we can see where it took off right here. And we only peaked at 86% airtime usage, but during the packet capture, we weren't even using all the airtime that was available to us. So the data rate that I saw, about 20 megabits per second, was probably due to our ISP here at the office. So here we can see MetaGeek Lab took up the most of the airtime. There are a couple of other SSIDs. These are probably hidden SSIDs. We can see that there's at least one other wireless network on our channel, but it didn't talk much. We took up the most of the time talking. If we drill down into it, we can see that our retry rate was 17%. We can see that there were 34 clients that we heard on this channel, and we can see that our effective data rate was 31 megabits per second. We had a nice, fast conversation. We only dipped down to 6 megabits per second about 2% of the time, but we spent the majority of our time talking fast at 24 megabits per second. If we click on, we can see that most of our time was quality of service data with a little bit of acknowledgement in there. So let's go ahead and click on the Packets tab, and let's take a look at what this process might have looked like. And maybe we will drill down into that device a little bit more. This is an ASUS device. We can see we actually got the OUI from that. We were able to identify who the manufacturer was. So let's go to the Packets tab and take a look. We can see that we weren't using block acknowledgements here. It was not utilizing block acknowledgements. We were going data, acknowledgement, data, acknowledgement, data, acknowledgement. We can see where that conversation was occurring. We can also see what direction the frame was going towards. Was it going towards the access point, or was it going towards the client? And we can see that the client was using a faster data rate to transmit to the access point than the access point was replying to. It was typically using a lower data rate, like 24 megabits per second. But we can see that conversation unfold, and we can see, now that we have this highlighted, we can see it where it's highlighting that in the spectrum. So let's go ahead and open up some sample captures that are included with IPA. If you're watching this webinar to kind of evaluate IPA to see if this is a tool that you want or not, you can do this too by downloading IPA on trial. I'm going to open up cafe.pcap. This is a previously saved PCAP file. Let's take a look at what happened during cafe.pcap. Now, the first thing I like to point out is the amount of time that we used sending beacons and probe requests. Remember, all this purple stuff, these are all just devices beaconing, saying, hey, I'm a network and I'm here. And we can see all of these, we're spending all of this time sending their beacons. In fact, we can filter that out by getting rid of the control frames and the data frames, and then we can get rid of all the management frames and only add the beacons back. It's amazing how, when you look at the amount of time that these use, if you use virtual SSIDs on your network, I've seen people do tests where they saw how many virtual SSIDs can I add to my access point before the beacons consume all of the airtime. And it doesn't take long. You can consume all of your airtime with beacons in as few as 5 or 6 virtual SSIDs on your access points. So you have to watch out for that. We've applied all of these filters up here, and we can click on individual filters to get rid of them. But what I'm going to do is click down, and I'm going to enable my management frames, my control frames, and my data frames again. So we're going to bring all those frame types back so that we can see what happened on the course of this network. So let's say that you have a client who comes to you that's having some trouble, and you want to take a look at their device specifically. We can actually filter by client vendor. For example, we can filter out all of the Apple devices here. So let's take a look at all the Apple devices to see how much time they consumed. We can see the Apple devices consumed this much airtime. So this makes it really quick. If somebody brings you an Apple device and says, hey, I'm having problems, you can start a packet capture. You can capture that data and then filter by Apple to take a look at those specifically. So we can see that under this network, Bronco Guest, this capture was taken down at Boise State University, which is only about a mile away from MetaGeek. We can see that there was an Apple device here, and we can drill down into that and go take a look at the Packets tab to see exactly what was going on. In this case, we can see that our retry rate was 83%. We have a ton of retry flags here. This was not a fast and successful conversation. This conversation involved a lot of retransmissions, and that's something that we might want to look into. The other thing that we can do here is if you just want to get a look at the overall health of your network, you can select your network and then you can visit the Analyze tab. So now we have starred all of the networks that belong to Bronco Guest, and we've given you some hints as to what might be going on. Now, if we were to only star one of these, I'm going to notice a few things. First, I'm going to notice that there is a high retransmission rate here. We've got two devices that are retransmitting their frames all the time. Well, why is that? We get the MAC addresses so that we can hunt them down, and maybe we've got a Wi-Fi chipset issue. Maybe it's just a driver that needs updated. Maybe we've got overlapping interference. Maybe we've got networks that are partially overlapping and they're corrupting those frames so that we have to resend them. We might also have some non-Wi-Fi interference as well. We give you as many expert tips as we can from the packet analysis side of things so that you can more quickly figure out what's going on in your wireless network. Finally, the last thing I want to show you, one of my favorite things, is the ability to export to Wireshark. You can send frames to Wireshark. You can filter down with our powerful filtering tools. You can filter by data rate, RSSI, frame type, MAC address, client vendor, and even SSID or AP vendor, and you can send those to Wireshark. So what I'm going to do is click on a network. Let's find one that's got a nice mix of different frame types. So we'll click on this one. So now we have drilled down into this. So then let's click File and then click Send to Wireshark. And let's send all of this data over to Wireshark. We wanted to make a tool that complemented Wireshark. And so that's why we built this ability into Eye P.A. And I've applied a custom color filtering rule here so that we've got the same colors as we would see in Eye P.A, which makes it really easy to bounce back and forth between these tools. You can really drill down into your frames with one of your old standbys, with your favorite open source and free packet analysis tool. Eye P.A ends up being a powerful filtering tool for use with Wireshark. If you want to try out Eye P.A, if you want to download it on trial and take it for a test drive, you can. You can download it at metageek.net/downloads. Also, we have a free Wireshark color profile available for you if you'd like to enable that for use with Eye P.A. There's the URL right there. I'll leave that on the screen for just a second. And at this time, I'd like to open up the webinar for questions. Any questions about this tool? Feel free to use the question tool and let me know what your questions are. If you have any questions after the webinar has concluded, feel free to contact me. I'll put my contact information up in just a second. Here's pricing for Eye P.A. You can capture from an AP or Mac or from Linux. Eye P.A is $4.99. If you're in Windows and you need a special capture device, you can buy Eye P.A plus the Air PCAP NX together, and we give you a bit of a break. We give you $50 off when you buy them together, so the total ends up being $11.49. The Air PCAP NX allows you to create PCAP files in Windows. It's a full 2x2 802.11n chipset, and you can even do 802.11ac analysis with this tool, because all 802.11ac frames are sent at 802.11a and 802.11n data rates. So we can actually perform full 802.11ac airtime calculations with an Air PCAP NX and Eye P.A. If you capture from a Mac, you of course get all those 802.11ac frames, which Eye P.A fully supports. A question I have is, will this video be available for download? Yes, it will. Give me about 12 hours or so. I hope to have this video posted to our knowledge base within about 12 hours. So head over to our knowledge base at support.metageek.net after a day or so have passed, and search for the wireless packet analysis webinar, and I will get that posted on the knowledge base for you, as well as the slides as well. So just keep an eye out for that. If you can't find it after 12 hours have passed, then feel free to contact me at support.metageek.net. I will get you a link for that. All right, if there aren't any further questions, then I think we'll go ahead and conclude the webinar. Thanks for joining us today. Packet analysis is a ton of fun. In my opinion, this is one of the most fun webinars because the client arbitration process and talking about airtime and getting to show Eye P.A is one of my favorite things. I hope that you learned how to use Eye P.A, and if you're thinking about buying Eye P.A, I hope this gave you the information that you need to make a purchasing decision. Thanks for attending today, and I hope to see you in a